the last 8 bit or the lower order 8 bits of the flag register. The flag register is a 16-bit register, and lower order 16-bit, lower order 8 bits of the flag register are the conditional flags. So we are shifting using load the LHF command. We shifted everything. What was the command? LHF only. We shifted our LHF load AH from lower byte of flag. That we shifted the conditional flag to AH register, and we have seen what is happened in the happened to the flag registers. Okay, so basically what we did is 8-bit addition and subtraction. So today what we are going to do is we will discuss about 8-bit multiplication, division, then the program, then 16-bit addition, subtraction. Everything is straightforward only. Okay, so let me show. So here in multiplication, we will use another command like MUL command. Okay, let me explain that. So for multiplication, we will use this command mul or mul. So let's start with 8-bit multiplication. So 8-bit multiplication. One second. So please admit that Nagaraj also is TA. So he is not able to join just. Who is the admin? Please allow him to join. Let me. One second, let me wait for him to join. Yeah. Okay. So we will first we will do 8-bit multiplication. So we are using the what type of numbers it is, hexadecimal numbers only. So if you are multiplying two hexadecimal 8-bit numbers, say something like FF and another two FF, if you multiply these two 8-bit numbers, we will get a 16-bit number. So when we multiply 8-bit numbers, the result will be a 16-bit number, and the result will be, so it is something like this operation is something like one of the value. This is one value. There are two numbers are there. One value we will store in the AL register, and the second one we will copy paste. We will store in the BL register. Okay. First value we will load in the AL register, and the second one we will load in the BL register, and the syntax is mul BL. Okay, so the meaning, these both the numbers are 8-bit numbers only, so we need only AL register and BL register. And when it is when this command is executing mul BL, then what are the content of BL register and the content of AL register get multiplied, and the result is stored in the result is actually a 16-bit number, and the result is stored in the AX register. Okay, the result is stored in the AX register. Is in the AX register. So AX register is actually consists of AL and AH. So likewise, the lowest 8-bit is stored in the AL register, and the highest bit is stored in the AH register. So that is the procedure. That is the result will be shown like this only. And if you want, okay, that is the thing. Okay. Then if it is 16-bit number, suppose if it is a 16-bit number, like if it is 16-bit multiplication, what will happen? If it is a 16-bit number, then one of the then when we are multiplying to 16-bit number, the result can be a 30-bit, which is higher than a 16-bit also. So it can reach up to 30-bit, 32-bit number also. So there is what will happen. So it is something like we are multiplying two numbers, say F. So this is number one and number two. What we will do is we will store this value in AL register, sorry, AX register, and another this one BX register. And if you are using the command mul BX, then the content of dx will be multiplied with the ax. So the result will be, instead of the 16-bit, we will get something higher than 16-bit. So the lower 16-bit will store in the ax register, and the highest remaining values will be stored in the dx register. So there is these two are segment registers, ax and dx are general purpose registers only. So AX register, this lowest 16-bit numbers will be stored in the AX register, and the highest values will be stored in the DX register. Okay, so this is the 16-bit multiplication. Similarly, 8-bit 8-bit division, so 8-bit what 8 in addition and subtraction, the method is same only. When there is a when we are adding to 16-bit numbers, there might be a carry will be there. That carry will affect the carry flag only, but result will be stored in the method is similar type of the previous case only. Add comma b means the result will be stored in the first the first register. Okay. Then 8-bit division. So 8-bit division means, so when we are dividing the first number, the numerator number should be higher than the denominator number. So it is 8-bit division means the first number may be a 16-bit number, and the dividing number, the dividing number is 8-bit number. Okay, and so when we are dividing like this, the command is div command only. So for division also, one of the number will be stored in the AX or AL register. So this is a 16-bit number, so it is stored in the AX register, and this is stored in the BL register. And when we are using this command, a divide div bl, AX content will be divided by BL, and the result, the quotient will be stored in the AX register. The quotient will be stored in the AX register, and the remainder is stored in the DX register. Okay, the quotient will be stored in the AX register, and the remainder will be stored in the DX register. So the thing take care about it. The first number should be greater, is a 16-bit number, and the smaller number will be a 8-bit number. So what you can do is in your calculator, these you can do these the hexadecimal addition. So addition, subtraction, hexadecimal calculations you can do in your calculation in your calculator. So you can take two numbers and multiply these two numbers, and you can find the result, and you can check whether the through the program also whether you are getting the same thing only or not. So, and similarly the division also you can do the same thing. So everything you can check it using your calculator. So we are not going to discuss about how it is performing. That is already, how this hexadecimal number system, that's multiplication, division, etc. are happening. That you are, I hope that you already studied in your digital electronics class. Okay. So similarly, the 16-bit division, the first number should be a 32. That number should be a 32-bit number, and the second number is a 16-bit number. And this in this division, actually, this 16-bit division, the lowest 8-bit is stored in the AX register. In AX also, AL and AH is there, and the highest numbers are stored in the DX register. Okay. Similarly, the second number is 16-bit number is stored in the BX register, and when we are dividing this number with this number, the quotient will be stored in the AX register and in the DX register. Quotient will be stored in the AX register, and the remainder will be stored in the DX register. Okay, so we will start with this 18-bit, sorry, 8-bit multiplication. Then we will, yeah, then the remaining things also we will do. So, okay, then the program and everything will be explained by Nagaraj. So let me stop presenting. He will start present. Nagara?
Yes, sir. I am
Yeah, okay.
sharing it.
Yeah, okay.
Sir, first I need to take a 8-bit multiplication, right, sir?
8-bit multiplication. Then then depending on your suitability, whether you want to show 8-bit division, that way, whichever way you can proceed, you can proceed.
So first I will explain the program, and then I will explain the
Okay,
output,
okay.
sir. Okay, side by side I
Yeah.
will show the
Okay.
results. Students, before going to our 8-bit multiplication and division, first you have to know something how to transfer the data from a memory location to a register, and a register to a memory location, because this kind of instruction may be used in program. Okay, so mostly this kind of instruction will be available in the program. So we need to know how to transfer the data from memory location to register, and also from memory location to register and register to memory location. Okay, and for that then only you will give the input data, and you will verify the output data. Okay, see, for example, so this will be the memory location we will mostly used in our program. Okay, mostly 8500. Okay, 8500 is a memory location. Okay, so this 8500 is memory location, it will hold only 8-bit data. Okay, so for example, yes is a hexadecimal number. Okay, yes is a hexadecimal number. So yes is a 4-bit lower 4-bit number, and this yes is a higher 4-bit number. Similarly, see, this 8501 is a one more memory location. Okay, so all the memory location will handles only 8-bit numbers. Okay, so similarly, this T is lower 8-bit, and this T is a higher 8-bit. Sorry, a lower 4-bit, and this is this T is lower 4-bit, and this T is a higher 4-bit number. Okay, so similarly, 8502 XX 8-bit number, 8503 YY 8-bit number. For example, see, if I want, if I want to move any content, see, if I want to move any content from AX register to the memory location specified. Okay, so before that, you need to specify some memory location like this. Okay, move SI comma 8500. Okay, so this, okay, what is the use of this instruction? Means we are assigning a memory location to the SI register. Okay, so move SI comma 8500 means we are assigning the value, okay, 16-bit value to the SI register. Okay, so this 16-bit value is nothing but an address value. Okay, nothing but an address. Okay, so SI is a 16-bit register. Keep in mind, move SI comma 8500. SI is a 16-bit number. This 16-bit number 8500 is moved to this SI register. So what is the use of this 8500 means? It's nothing but an address. Okay, then move within a bracket SI, within a square braces we need to put SI comma AX. Then what this instruction will do means, so see, AX is a 16-bit number, right? It is a 16-bit number. It is a 16-bit register. It is splitted in the way like this, AH and AL. Okay, it is splitted like this, AH and AL. Lower 4-bit is present in AL, for example 2 3, and higher order AH is present. Higher order is a 4-bit. Higher order AH is a higher order 4-bit, right? So maybe 5, 6. Okay. So this is the data which is already present in the AX register. Suppose if you want to move the content of AX to the particular memory location. So already you know the memory location which is assigned by 8500. Then how this 8-bit how this 8-bit transfer, sorry, 16-bit transfer will do. Okay, so see, move within a bracket si comma ax means first it will load lower 4-bit number to the memory location specified. So ax. Okay. So first it moves 23 to 8500 and then it moves 56 to 8501. So this, it is done automatically. Okay, so the increment of this memory address, so because of this instruction it will increment automatically, but sometimes it will not increment it is not happens at every time. Okay, for example, if you want to move one more data, for example, move within a bracket of si comma bl. Okay, see, first we are specifying some data, okay, some memory location, and we are moving ax register to the memory location which is specified as 8500. First ax register split into ah and al. Lower 4-bit, sorry, lower 8-bit is moved to first memory location, higher order 8-bit moved to the second memory location. Suppose if you want to see, suppose if you want to do this operation, means what happens? Move si comma bl. So you know already si is 8500. If you perform bl, okay, move the data. This is 8-bit data, right? So bl, for example, it is having 4, 5. Example means the content of 8-bit register, which is bl, is moved to the same memory location, that is 8500. So the content of bl is moved to same memory location. Okay, so see, if you want to move the bl to this memory location, means we need to increment the si by 2 times. Okay, see, if you want to move the content of bl in this place, okay, in this place, then you have to increment the content of si by 2 times. So inc si, inc si. So 2 times. So first si contains 8500. Okay, so 1 time increment means plus 1, 8501. Okay, then it becomes 8500 becomes 8501. Then one more increment si. Then 8501 becomes 8502. Okay. Then we have to move the value of bl. Okay. Then if you execute this instruction, then this 4, 5 will move here. Otherwise, it will move in this location. So that is a difference. Okay. So this kind of instruction will be normally available in the program. Okay. If you do any thing, your input data and output data will be collapsed. Okay. So keep in mind, this is a way how we are moving 16-bit data to a memory location and 8-bit data to a memory location. Okay, suppose, so this is a content, see, so this is a content, move cx comma 8 cx comma within the square braces si. Okay, so what this instruction will do means the content of si, okay, the content of memory location is moved to cx register, So this is 8-bit data transfer, sorry, 16-bit data transfer. Okay, so if it is there, cx means 16-bit. Okay, then the content of si, you already know, initially we declared 8500, right? Then we incremented 1 times si, so it becomes 8501. We increment 1 more time, it becomes 8502. Then see, the content of 8052 is moved to cx register. Then see, then 8502, it will move to cl register, and whatever the value which is present in the 8503 is moved to the CH register. Okay, always lower order moves first and higher order moves second. Okay, see, move cx comma within a bracket si means, okay, the content of memory location is moving to the register. Okay, but how it moves, in that particular memory location we are having 8-bit value, right? That 8-bit value should be moved to lower 8-bit, lower 8-bit of that particular register, and the next memory location content is moved to the higher 8-bit of that particular register. Okay, so this is what the data transfer operation. For example, suppose, suppose instead of cx it is having dl. Okay, it is having dl means then we are performing same move operation, but we are performing 8-bit uh, we are performing 8-bit data transfer. Okay, so the content of si, okay, we know the content of si is now it is 8502. We are moving to the dl register. So you know dl is 8-bit number. Dl is a register which holds 8-bit value, right? So only, this operation it will take only this value and moves that value to the dl register. Okay, so it will not increment, sorry, it will not move 16-bit number. It will only move 8-bit number. Okay, suppose if it is dx, then it will take first value and it moves to dl, and automatically without any instruction, okay, it takes second value and moves to dh register. Okay, so this is done automatically. Okay, it is depends upon the instruction whether it is a 16-bit or 8-bit. Okay, this memory operands, this memory transfers and all. Okay, so with this example I am moving to the code. Okay, so initially I will perform 8-bit multiplication. Okay,
So
so 8-bit
basically, one second, Nagaraj.
yes,
Basically, we are
yes,
storing one 8-bit number in this 8500 memory location and another 8-bit data in 8501 location. And the result is stored in 8502 location and 8503 location. Right?
yes sir, mostly depends upon the input and output. This memory location will vary.
Okay,
So,
okay.
for
But
example, if it is 8-bit means if it is 8-bit addition means first 8-bit data stored in this location and second 8-bit data is stored in this location. So,
yeah.
8-bit plus 8-bit is again 8-bit data. So, it will be in third memory location. So, if it is 8-bit means this memory location is enough. But if you go for a 16-bit plus 16-bit, this memory location will extend, depends upon the input and output values.
Okay, so here we are doing 8-bit multiplication, so the result is a 16-bit result, and we are
Okay.
storing in 8502 and 8503. So what we
Yes,
are
sir.
initially we are storing all the data, these two data 8500 in two memory locations. This 23 or some data, 8-bit data in 8500 and 850 in 8501, another 8-bit data,
Sir,
and
once
those.
again, sir. Yes, sir. So this is the actual data we are going to perform. You just
Okay.
explain, sir.
Yeah, so we are storing this FF 8-bit data in 8500 location and 1, 2 in 8501 location. And from that location, from the already stored data, we are taking to AL register and BL register. Okay, so the content of SI is this is stack index stack register. So the content is of this 8500 is moved to AL and 8501 is moved to BL. Then we are just performing MUL BL. That means this FF and 1 2 are multiplied, and the result when you are multiplying FF and 1 2, let me check it. The answer will be when you multiply FF and 1 2, you will get 1 1 EE. I think 1 1 EE only. Yeah, 1
Yes,
1
sir.
EE, you will get 1 1 EE as the result. So it is a 16-bit. So that 16-bit, the lowest 8-bit will be stored in 8502 and next will we are storing the result in these two locations. It is so the result will be present in the AX register. That 16-bit after multiplication, the result will be in the AX register. That from that AX register we are moving to some other location. So the basically we are taking two data which is stored in two memory location and storing the result back into some other memory location. So for simplicity, we are taking consecutive memory location, because otherwise we need to specify that memory location. So here, if we can simply use the command increment to go to the next memory location.
Shall I show the output, sir?
Yeah, you can show the program running.
Okay,
out
sir.
of play. So those who have any doubt related to this hexadecimal multiplication, you can use. I will. Okay. What I will do. I will take one internet link. I will share it here. You can go to this website and you can see the can perform your hexadecimal multiplication, division, addition, everything, and you can check it also online.
So this this instruction is common to change the directory. So after changing the directory, I have a program. So I am going to open the program with the edit command. So if you guys don't remember that steps means, please follow here. Edit program name. So this is a program. Okay. I think you already know this is a opening and this will be the closing statements or syntaxes. So only this is a kind of program. Okay. See, first.
So Nagaraj, you can copy
Yes.
paste the same program in the comment box so that everyone can access.
One second, sir. So actually, this is a code. Okay, I copied and I pasted in a chat box. Okay, but I don't know whether it will be again copied and will be pasted in this DOS box. You have to type that, I think so. See, this is origin. Okay, so org means my program location will be in 1000h. Okay, 1000 starts from 1000. And this will be the first instruction, as I said, right? Move si comma 8500. The content which is 8500 is moved to si register. Okay, si means source index. Okay, so move si comma 8500 means we are moving the content 8500 and we are to the si. Now si is equal to 8500. Okay, then move si al comma within a bracket within the square braces of si. So the content of 8500 is moving to al register. Okay, the content of 8500 is moving to al register. Then we need to increment one times. Then 8500 we need to increment the content of si, right? So si is already having 8500, so we are incrementing one time. So 8500 plus 1, which is equal to 8501. Then in second memory location, one more data is we are going to give. Then that data is to be moved to BL register. So BL is a one more another 8-bit data. Okay. So 8500 is a one 8-bit data, and 8501 contains another 8-bit data. So we are performing multiplication operation, mul BL. As said, so mul BL will multiply the content of BL register with AL register. Okay. If it is 8-bit means directly it will multiply with AL. If it is 16-bit means mul BX means it will multiply with AX register. So since I am using 8-bit data mul BL, this 8-bit data is multiplied default with AL register. So multiplication of AL and BL both are 8-bit, right? So it will give 16-bit number. Okay, that 16-bit, in order to store that 16-bit, so it that 16-bit results will be available in AX register. Okay, so after multiplication, this processor will default put that value, stores the result in AX register. Okay, so in order to see that content, that output, so again I am incrementing the SI to 1. So initially it is 8500. It, one time means 8501. Second time means 8502. Okay. So in 8502, I am storing the value of AX. So what happens? I told, right? Move SI comma AX means first lower order AX, that is AL, is stored in this memory location, that is 8502. Then higher order AH is stored in next memory location 8503. Okay, so I already explained, right? So that is a major operation we are performing. So I am saving the content, exit. See, next one is MASM. As a multiply.asm. I'm not getting any errors. So I'm proceed with second command, link multiply dot object file. Then again there is no error. Then debug multiply dot exe. Okay, if you press multiply debug multiply dot exe, it will show one hyphen. Then we need to provide the input. Okay, then we need to provide the input. Okay, one second. Please, everyone, guys, please make a note of it. Okay, you just please make a note of it. In 8500, I am placing the value of FF. Please note it. 8501, I am moving the data. Sorry, I am giving the data 1 2. So this multiplication will already stores the result in AX. That value will be again storing that value from a register to this memory location. So EE is a AL register. AL content is moved to this 8502. This will be the result. This is a multiplication of these two will give this 16-bit number. So 8503 is having higher order 8-bit number. So please copy this and we will verify the results now. Okay, so first I am giving the number. First one is, what is the number? FF. Okay, I'm giving FF 8500. If you press space bar, then it is going to second memory location. Okay, then in second memory location we are giving one more data, that is 1 2. Okay, FF12 is a two 8-bit numbers. Okay, which is stored in 8500 and 8501. Then if you press space bar means it goes to another memory location 8502. So for instance, I am giving 00 for, I am clearing that memory location. Next 4 consecutive memory location. Then I am pressing enter. Okay, so after giving input value, which is FF which is stored in 8500 and 12 which is stored in 8501. Okay, then it will defaultly takes that from the program. I am executing the program, right? So D is equal to 1000. So the program execution done. Okay, program terminated normally. So what the program does means it takes FF and moves the value to AL. It takes 12 and moves the value to BL, performing performing 8-bit multiplication, and results are stored in AX, and again we are taking that value to next memory location 8502 and 8503. See again, um, 8500. So first value is F of 8-bit data, second value is 12. See, third value is EE, and fourth value is 11. So it means 8500 contains FF, 8501 contains 12, 8503 contains EE, 850 8502, 8503 contains 11. Okay, so EE it comes from AL register, and 11 it comes from AH register. Okay, so this is an multiplication operation.
One second. So in the earlier operation, students can see that initial value of the 8500 register was 6F, that we replaced with the FF. Similarly, 8501, the initial value was 70, that we replaced with the 12, and 8502 it was 65, and 8503 it was 6E. We replaced everything with those two values with the 00. Then when we executed the program 8501, that data is already there in the that is one of the input value, and the second one is 8501, that is a second 8-bit number, and the result we stored in the 8502 and 8503 registers, not registers, memory locations. So that we can see. What you can do is you can instead of these two values, you can give some other values, and also you can verify the thing. So what you can do is you can, instead of if of such a type of bigger value, you can give some small values like a 03, 02. That those two are 8-bit numbers, so the result will be also 8-bit number. So you can see, finally you can verify that 8503 memory location will be 00 again. That you can verify.
Students, any doubts in this program? So please ask.
So if you have any doubt, just raise the question. Otherwise, it will create problems too when we are going for 16-bit numbers.
If there is no doubt, shall I proceed, sir?
Sure, you can go to next which is division, or what you are planning.
It's up to you, sir. Shall I proceed with multiplication, sir? 16-bit multiplication.
Yeah. You can go.
Okay. See, students. So now we are performing 16-bit multiplication. Okay. So in 16-bit multiplication, first I am taking a 16-bit value which is present in AX register. Okay, so see, so AX register contains 16-bit value, right? So this 16-bit value is splitted into lower 8-bit as 15 and upper 8-bit as 15. Okay, so nothing but, so this is the actual value. Okay, so 1515. Okay, so this is actual value. Okay, so we are taking this value from this memory location 15. Okay, one second, 15. So from the memory location 8500, I am taking the first value, I am pasting here. Okay, so the first 8500 is moved to AL register and 8501 is moved to AH register. Okay, so first 16-bit data is ready now. Okay, next 16-bit data. So next 16-bit data is C. 4 5 and 2 3. Okay, so 4 5 and 2 3. So this is a next 16-bit data. So I am taking this data, I am moving to BL register and this data to BH register. Okay, so this is one 16-bit date number and this is another 16-bit number. So one 16-bit number is stored in AX register and another 16-bit number is stored in BX register. Okay, now we are having two 16-bit numbers. Okay, so if you perform multiplication of two 16-bit numbers, then you will have the result of 32-bit number. Okay, so that result, okay, so that result, see, multiplication of these two and these two will have 32-bit number. Okay, as I said, lower order 16-bit is stored in AX register and higher order 16-bit is stored in DX register. Okay, so this is a lower order 16-bit and this is a higher order 16-bit. Okay, so this is what we are going to perform now. So again I am saying first I am writing the program. Okay, after writing the program I need to give this is an input. Okay, so in 8500 I am giving 15, 8501 15, 8502 45, 8500 23, all are hexadecimal numbers. Okay, so by the program it directly this two values goes to AH and AL AX register. So these two value directly goes to BX register. Okay, it will perform multiplication. Okay, these two AX mul BX means it will perform multiplication. After the results will stored in the lower order 8-bit is stored in lower 16-bit stores in AX register, higher order 16-bit stores in DX register. Okay, so then again I am retrieving that value from, I am again moving that value to this memory location, consecutive memory location. 8500 it stores AL, 8505 it stores AH. This becomes lower order. 8506 having E7, 8507, 06 having E7, 8507 having 02. This is higher order 16-bit. Okay, so please make a take a snapshot of this value. So I am giving this value in program. Okay, so please take a snapshot of this one. So let me go to this program. Okay, edit mul16.asm. This is my program name. Okay, see, this is a code. So again, this is a starting and this will be the ending statements. Okay, and see, this is my origin. Okay, I am starting my program in 1000. This is a statement. This is a syntax, that is move si comma 8500. Okay, so this value is moved to yes. Now si is equal to 8500. Next, move ax comma within a bracket of square braces of si means the value of 8500. Okay, the two memory location, that is 8500 8501 is moved to AX register. First it fills AL and next it fills AH. Then I am incrementing the content of SI by 2 times because in order to get the second value. Okay, so initially it is 8500, right? So it becomes 8501, 8502. Now from the memory location 8502, okay, from the memory location, one second, from the memory location 8502, I am moving the content to BX register. Okay, so 8502 moves to BL, 8503 moves to BH. Okay, then I am performing multiplication operation, okay, by using this instruction. Okay, sir,
Yeah.
sir, whether the screen now it is visible, sir?
Yeah, it is visible already.
Then for seeing the results, I am incrementing the SI register by 2 times. Okay, so initially it is 8500. 2 times means 850102. Sorry, 0102. Next 0304, I think 04. Yes, 04. So I am moving the content of lower 16-bit product number. Okay, the output result of lower 16-bit number, which is stored in AX, right? So it should be moved to SI. So SI is now 8504. Okay, which contains AL, which is moved to AL content is moved to 8504. Then content of AH is moved to 8505. Then I am incrementing 2 times SI. Okay. Then I am moving the higher order 16-bit higher order 16-bit result. Okay, so higher order 16-bit results I am moving to 8506 first and then 8507 next. Okay, so so this is a program. Okay, saving the program.
Please give the program to the students also. Just copy paste and paste it in. Copy and paste
Yes.
it in the comment box.
So I am having executing that program mathsum mul16.asm. I am not getting any error. Proceed with second command, link program name dot obj, not having any error. Then I am proceeding with next command, debug space program name dot exe to left with p. Then I am going to store the two 16-bit numbers. Okay, as I mentioned. Okay, e space 8500. Okay, so please write it down. Okay, students, please write these values. Okay, in rough note. Okay, so now we are going to verify this one. I am giving 15, 15, 45, 23 as an input. I will get this results. Okay, in 8504, I should have A9, A-D, E702. Okay, please make a note of it. Okay, I think you written this value, right? So I am proceeding. Okay. Sir, if I am keeping this side by side console, whether it is visible, sir? Otherwise, I go for full screen. Students,
Your,
please respond.
yeah, your this wait file is visible, but the other one, that docs box is not clear.
Okay, then I will proceed with this. Okay, so I am replay. First, I am giving 15. Second data is 15. Third data is 45. Next data is 23. Okay. Then 3 is equal to 1000. So the program terminated normally. So it indicates the after getting the this as an input, it executes and it stores the result. Okay, so let me check that value. E8500. See, first data is 15. Second data is 15. This two stores in one. This two act as a 116-bit number. 45 and 23. Okay, this will act as a second 16-bit number. The result is, as I said, 8504 stores A9, 8505 stores 8D, 8506 stores E7, 8507 stores 02. Okay, so if you multiply two 16-bit numbers, you are getting 32-bit number. The 32-bit number first AX, the lower 16-bit having it is stored in AX, and higher order 16-bit stores in DX. Okay, that's all about this program. So if you have any points, please add it, sir.
No, I don't have anything. Let me. What about students? Anyone have any doubt?
Students, if you have any doubts, please ask me. Otherwise, it is very difficult to when you go for division and all, that moving data, that is data moving the data transfer instructions. If you have any doubts, please ask me.
Anyway, we can wait for 5 minutes. Let the students perform the complete the experiment, and later we can do the remaining division of operation, division, or 16-bit addition, whatever it is.
Okay,
Let's
sir.
wait for 5 minutes. If you want to go somewhere also, you can go and come back in 5 minutes.
Okay, sir. Okay.
Yeah, if you want to drink some water or something.
Okay, sir. Fine.
So we will continue after 5 minutes. We are waiting for you people to complete the program. Okay, we will start it in 2 minutes. So if anyone, we are believing that everyone got the answers. Okay, then we can start.
Shall I proceed, sir, now?
Yeah, yeah, okay, we can start again. The which one we are planning? Division,
Uh,
8-bit division, or
Whether I proceed with division, sir, first?
yeah, you then 8-bit division. Yeah, yeah, we can
And,
proceed with 8-bit division. 16-bit
uh,
addition
uh,
anyway, it is straightforward only.
uh, okay, sir. If you want to teach 8-bit, 16-bit means first I will teach that and I will come here. No issues.
We can go ahead with the 8-bit division first,
Okay, sir,
because that
fine.
is the remaining from the 8-bit category.
Okay, sir. Students, now we are going to perform 8-bit division. Okay, 8-bit division. So why I am saying it is 8-bit means it is a 8-bit divisor. Okay, so there is a notion of that 8-bit division. So this is 8-bit division. So 8-bit division means, so we are having 8-bit divisor. Here the divisor is FF. Okay, please, if I show this some examples means please note down. Okay, so I am only performing with data 1. Okay, while you submitting your records you have to perform at least for data 2, 3 and 4. Okay, at least 2 examples you have to do. Okay, so I am performing only for data 1. So similar kind of table you should be drawn. Okay, with data 2 and data 3, some examples. Okay, we will verify that also. So if you perform 8-bit division means, see, 8-bit division means this is divisor and this is dividend. Okay, so first we are entering. Okay, we are putting the some values in this memory location, that is 8500, 8501, 8502. This is nothing but a dividend, and this is divisor. Okay, here it is 3412, right? So 3412 in the sense, first I am putting lower order 8-bit, next higher order 8-bit. So which is nothing but AL and AH. So I am storing dividend in AX register. Okay, so first I need to put lower order in this AL register and higher order 8-bit to AH register. So these two data forms 16-bit data, AX register. Okay, then I am moving the data from 8502 to this memory location BL register. Okay, For that, I need to increment one time, and then I need to move the value of 8502 to BL register. Okay, so after moving, okay, so I need to perform the division by dividing the dividend, that is AX register, with the content of divisor BL register. Okay, so dividend is 16-bit, divisor is 8-bit, so I will get 8-bit quotient and 8-bit remainder. Okay, so this perform, okay, div BL, it automatically stores the result, that is quotient in AL register and remainder in AH register. Quotient in AL and remainder in AH. Now, in order to verify the results, again I need to transfer the data from this registers to memory. Okay, for that I need to use some data transfer operation. It will move the content of AX register to the memory location. So while moving also, it will first place the lower order 8-bit and higher order 8-bit. Okay, so this is the division operation. So the lower order is nothing but quotient and higher order is nothing but a remainder. Okay, so please see this table, okay, and please make a note of it. Now we are going to perform in console. Okay, so please make a note of it. We need to verify this one. Okay, so I am going to edit divide.asm. This is my program. Okay, so as you know, this is a starting and this is a ending statement. Okay, then I am starting a program with 1000. Okay, then assigning a memory location to SI register. Then I am moving the content of 8500 to AX. So this instruction will perform two data transfer operation. Keep in mind, this instruction will perform two data transfer operation, which is nothing but moving the content of 8500 to AL register 8-bit and moving the content of 8501 to AH register. So this will perform two data transfer operation, moving two 8-bit numbers to AL and AH. Okay, then in order to get, this is nothing but a dividend, right? So dividend is stored in AX register. In order to get a divisor, I need to increment the memory location to 850 8502. For that, increment SI means 8500 becomes 8501. One more SI, increment SI becomes 8501 to 8502. Now SI contains 8502. So I am moving the content of SI, that is content of memory location 8502 to BL register. Okay, so this is 8-bit. Okay, this is 8-bit. Only one data transfer operation will done. Okay, nothing but it transfers the data from the memory location 8502 to the BL register. Okay, this performs two data transfer operation. This performs only one data transfer operation. Okay, so this is dividend and divisor. So after that, I am performing division. So this division div BL, okay, so well, what it performs means it divides the AX register, okay, AX 16-bit register with BL 8-bit register and stores the quotient in AL register and stores the remainder in AH register. Okay, quotient in AL, remainder in AH, so which is nothing but AX register. So in order to view the output, so I am incrementing the content by 1. So why I am incrementing means because this location will contain BL, right? So I won't disturb that one. So I need to increment one time. It becomes 8502 now. So I am moving the content of AX to SI. So again, this will perform two data transfer operation. First, it moves AL, that is quotient, to 8502, and next it moves remainder, that is AH, to 8503. I think I already shown the data, right? So please keep in mind, I'm executing this one. Asm divide.asm. I'm not getting any errors.
First, you just copy paste the program also in the comment box. So the students
Yes, sir.
can.
Link y dot obj next debug exe. Then I need to provide an input. Okay, so to provide the input, I need to use E8500 enter. So then in 8500, I am it is already having the value of 6f. I am changing with 3f. Sorry, 34. So 6f is replaced by 34 space bar, then 1 2. Then 70 is replaced by 1 2. So this 2 becomes a dividend. Then I need to provide a divisor. So 6 5 is replaced by ff. So this is my divisor. So that's all. Enter. G is equal to 1000. Then I need to verify the results. Okay. So E space 8500. So first 34, 12. So these two becomes dividend. FF is a divisor. Okay. I am not nothing but 1 2 3 4 1 2 3 4 divided by FF. I am performing 1 2 3 4 divided by FF. Okay, if you have calculator, you just check that. Okay, 1 2 3 4 divided by FF. I am getting 12 as quotient and 46 as remainder. Okay, please check that. Okay, so if you have calculator, you just check that 1 2 3 4 divided by ff, you will get 12 as quotient and 46 as remainder. So this is 8-bit division. Okay, students, do you have any doubts? Students, any doubts? uh, shall I proceed with 16-bit division, sir?
Wait for 2 3 minutes. Let the students to complete.
Okay.
Yeah, hope that you are following. Then, if there is no doubt, we will move to the next program, 16-bit division.
Students, please make a note of it. So this is 16-bit division. Okay. So this is 16-bit division means that is having we are dividing 32-bit number with 16-bit number. Okay. So this 32-bit number, right? So it will be it is having like this combination. Okay, as Sir said, actually Sir informed, right? So it is in B H B L A H A L. Okay, so first I am in some memory location I am giving some value. I will explain what is this value and all. Okay, so in 8500 I am placing E60102 8502 AA 8D1515 and all. Okay, so what the program does means, first I am moving higher 16-bit number. Okay, in 32-bit, okay, 32-bit is split into, okay, 32-bit is split into 16 plus 16, right? Okay, so this 16 is nothing but it is stored in dx. Okay, this 16-bit is stored in this dx, and this lower order stores in ax. Okay, so for first 16-bit number, okay, this is a 16-bit number. Okay, this value should be moved to dx register, right? So always keep in mind, always you should move lower order bits. Okay, e6 it should be moved in here. Okay, so this is e6 data. We need to move that to DL, and this is data we need to move to DH, and this data should move to AL, and this data it should be moved to AH. Okay, then you are having, so this is nothing but your 32-bit data, 32-bit dividend. Okay, 16-bit divisor. So this is 16-bit divisor. So nothing but it should be we are moving the content from, that is data from memory location to registers. So one more. Okay, so it's not coming. Okay, so which is nothing but BH BL. Okay, both are 15 and 15. So I am dividing the content of this with this one. Okay, then my result, okay, my result will stores in same register. Okay, that is result. I am dividing the content of, I am dividing 32-bit content with 16-bit number, so I am getting 16-bit as quotient and 16-bit as reminder. So quotient is stored in AX register, so quotient is stored in AX register, and reminder is stored in DX register. Okay, so please make a note of it. Please make a note of it, this value. Take a snapshot of it. Okay, we are giving this value in the program. Okay, so I am dealing with only one data. You have to verify for more number of datas. Okay, so that's what I am saying. Please take a snapshot and check the results. We are going to check the results now. Okay, so first edit division program. So please see, this is my division program. 1 second. So paste I pasted the code in a chat box. So this is my code, starting with origin. So this is my first memory location, moving the content of that memory location to dx first. Then I am incrementing the source index by 2 in order to get a second data. Okay, so the second data is moved to AX register, and I am incrementing the content of SI by 2. So from the statements, I am getting two 16-bit numbers. Okay, that is 32-bit dividend I am getting. Okay, now from this memory location, first one is 8500, 8501, 8502, 8503. Next, from 8504, I think, yes, from 8504, I am moving the data from that memory location to BX register. So 8504 and 8505, it is filled with divisor, that is BX. Okay, so after getting my inputs, I'm going to divide the content of AX with BX register. Okay, what happens means, if you are dividing 32-bit number with 16-bit number, the quotient is stored in AX and remainder is stored in DX. Okay, for getting my results, for storing the results from register to memory location, I am incrementing SI register. It is initially 8501, 2, 3, 4, 5. Okay, so 5, 6. So I am storing the value of quotient to 8506 and 8507, and I am incrementing by 2, 8507, 8506, 7, and then 8. Okay, so in 8508, I am storing the my reminder. Okay, 8508 and 8509. Okay, that is what I showed in that box, right? So input and output combinations. So I'm executing that code. No errors. Link division 16 dot click, and then debug 16 dot exe. So first I need to provide the 32-bit dividend. Okay, so E space 8500. In 8500, what is the data? E6. Next 02. Next AA. Next AD. Next 15. Next 15. Okay, so first four datas are 32-bit numbers. Okay, it is dividend, and next is 15, and 15 is a divisor. Okay, so after that I am executing the content, executing the program. So program terminated normally. So by getting these values, the program is executed and stores the result back to the memory location. We are going to view that. Okay, so E space 8500, enter. See, first data is E6, 02, AA, 8B. So this is dividend. These two are divisor. Okay, so quotient is present in AX register, right? So 3823. So 3823 means first you have to read like that, 2338. Okay, So 38 is stored in AL register and 23 is stored in AH register. So 23, 38 is quotient. Okay. Next 12 and 12. So both are 12. So 12 and 12 is your remainder. Okay. So this is 16-bit division. Okay. Why it is 16-bit means 16-bit divisor is there. That's what. Okay. Please, if you have any doubts, please ask me. Otherwise, do the program and verify the results.
So for all the examples, one of the example, the data bit should be taken from your roll number, all the students. You are not allowed to take common numbers. So one of the data is your roll number. For example, suppose your roll number is 10003, 1003, then it can be treated as a 16-bit number. So 10 is the higher bit, then 03 is the upper bit, lower bit. So these type of examples, you have to show it in your report. And different combinations of the same also can be used. Like suppose your roll number is 20B1003, then for taking a higher bit, if hexadecimal number, that 20B, that is also can be used. That 20B10, that 20B1 can be used like that also. Now, Nagaraj, then we can show the addition, 16-bit addition also.
Yes, sir.
So it is straight straightforward only 16-bit addition also, similar to that of 8-bit addition. And in all the operations, your flag registers will get affected. That you can verify by checking, by either shifting the content of that lower 8-bit to using LAHF command. Here we are showing with in a little different way.
Students, now we are going to perform a 16-bit addition. Okay, so 16-bit addition in the sense both numbers are 16-bit. Okay, so for both numbers are 16-bit means we are storing one value in AX, another value in BX. First value is AX, second value is BX. Okay, so we are putting some data in memory registers. Okay, that is 8500 is 11, 850 is 11, 8502 is 14, 8503 is 41. So this data is nothing but your examples. Okay, your examples, your data. So this is one data and this is second data. So if you put data like this means, okay, the first data is moved to AX register. It is moved by this way. First this bit, okay, is moved to AL, and next 8-bit, higher order 8-bit is moved to AH. So this is 11. Okay, 11 and 11. And next one is, please wait 1 second. So this is AH, AL. Okay, so AL is 11, BH is, sorry, AL is 11, AH is 11. Similarly, I am moving the content of this memory location to this memory register, right? So BH, BL. So BL is 14, BL is 14, and 41 is BH. Okay. Now we are performing addition, right? So now we are performing addition. So what? See, we are performing addition like this way. So 1 plus 4 is 5. Okay. 1 plus 4 is, 1 second. 1 plus 4 is 5. 1 and 1 is 2. So it is simple number. So I am getting direct value. So this here it becomes 25. Okay. And see, here it is 1 plus 1 is 2 and 1 plus 4 is 5, 52. Okay. So this is your result, right? This is your result. So what happens in addition? Okay, as already Sad told, right? So if you performing addition to 16-bit addition, the results is always held by AX register. Okay, AX register. Okay, that even though we are having the input, okay, that input is replaced by the output. Okay, so the addition of AX comma BX means first initially we are having one input in AX, another input in BX. The results will stores in AX then. Okay, so this is my result, right? So this is my result. Okay, nothing but this is AH and this is AL. So see, after performing addition, I am moving the content of AL, nothing but 25 to the memory location. Okay, so data transfer from register to memory, I am moving the content. Similarly, I am moving the content of AH to 52, AH to 52. If you are having any carry, okay, if you have any carry means this flag will be, sorry, this CL will be incremented. This CL is nothing but a 8-bit register. It should be incremented. Okay, if there is no carry, then this is, if it is not if there is no carry means 0 0. If it is carry means it becomes 0 1. Okay, this is one way of writing program. Otherwise, as I told, We can also see the content of carry by using LAH instruction. Okay, so I think this will be simple to you. Okay, let me execute this addition program. Okay, so I am adding 1 with 4114. Okay, I will get this results. Okay, please make a note of it. Okay, please write this data. Okay, and edit at 16.asm. This is my program. Okay, I will copy that program later. Okay, see, this is my origin. Initially, I am moving the content of 00 to CL. Okay, now nothing but CL is equal to 00 after executing this instruction. So what is the use of this instruction means instead of going to flag register, instead of moving the flag register content to AH, okay, so I am directly, I can able to visualize whether the carry is present or not by using this CL register. Okay, then I am getting the first value, okay, in AX register. Okay, move SI comma 8500, initializing the memory location, moving the content of first memory location to AX, nothing but 1 1. Then I am incrementing the memory location 2 by 2 times, so it will becomes 850, okay, 8501 and 8502. Okay, then I am moving the content of 8502 to BX. Okay, then two numbers will be transferred, that is 8502, 8503. Okay, then addition of AX comma BX. So I am adding the content of two registers, 16-bit register, and I am placing the result in 16-bit register. Okay, for seeing my results, I am incrementing this two content. Okay, incrementing this two S register content. I'm storing the value of AX. Okay, I'm storing the value of AX to SI. Nothing but result. Okay, I am storing the content of AX to the memory location. That is AL and AH are moving from registers to memory location. If see, this is an instruction. Okay, JNC. JNC means jump if no carry. Okay, jump. J stands for jump if, N stands for no, and C stands for carry. Jump if no carry. Okay, jump if no carry means if there is no carry, okay, it will move to this memory location. See, jump if no carry means it is nothing but a memory location. Okay, the address. Okay, if there is no carry means the program will directly comes here. Okay, so SKIP is nothing but a memory location. Okay, so J and C, if there is no carry, the program will directly comes from here, this location to this location. Okay, and increment INC SI, storing the what CL register content. Okay, I am increment SI by 2 times again, so it becomes 85045. Sorry, already it is 4, right? 5 and 6, 5 and 6. So the content of CL, which is already 0, right? Which is already 0. If there is no carry means 0 0 is present here, and we are moving the content of 0 0 to this memory location. That's all. In simple, see, these two, this is an instruction of getting first data. I am incrementing 2 times to get this second data. After addition, I am incrementing 2 times to store the result. Okay, again, if there is no carry means it will bring here. Okay, I am incrementing 2 times to store the carry. So this increment is based on this content. Okay, so if you are used AX means you should move 2 times. I am this data transfer is BX, right? So I need to increment 2 times. Again, this data transfer is AX 16-bit means I need to increment 2 times. If it is BL means I need to increment only one time is enough. Okay, so this is my program. What happens if carry is there? Okay, if no carry means it will skip the it will go from year to year. If it is carry, then if carry the condition is violated, okay, and it will executes the current instruction. Okay, so increment carry. So already CL is 0, 0. Okay, increment carry means 0, 0 plus 1. Okay, it will increment the content by 1. So CL becomes 0, 1, and that 0, 1 is stored in this SI register. That's all. If carry is present, okay, if carry is present, this condition violates and executes normally. Okay, if there is no carry, condition program transfer will happen, and moving that CL will be 0, 0, and it will be stored in memory location. That's all. Okay. So exit ASM, add 16.asm link, add 16.obj debug space, add 16.exe. So I need to give the first data, right? E8500. So first data is 11111441. Okay. Then G equal to 1000 and E equal to 8500. So first data is 1111. Second data is 1441. And the result is 2552. 0, 0 is means there is no carry. So addition of 1111 with 4111. You should read like this: 1111 and 4114. The addition of these two will give 5225 without any carry. So that is what it is 0, 0 there. Okay, you try with some other numbers. Okay. So this is 16-bit addition. Any doubt in this? Please ask. I will wait for 2 to 3 minutes, students. Please ask if you have any doubts. Otherwise, we will move on to 16-bit subtraction. I will wait for 3 to 4 minutes. If you have any doubts, please ask us. Even for a data transfer, if you have any doubts. Otherwise, it will become very difficult when the complexity of program increases. You can't understand that one. Okay, so please ask if you have any doubts. Clear it now. Students, shall we proceed with 16-bit subtraction? If you don't have any doubts. Okay, I am proceeding with 16-bit subtraction. Okay.
This time directly you can go to the program. Everything is same pattern only. You are storing two data in these memory locations, and only directly can go to the program. Nagaraj, you are muted actually.
So this is my 16-bit subtraction. Okay. So I am getting first data here. After two time increments, I am getting second data here. I am performing subtraction. Okay, a 16-bit subtraction. So if there is borrow means I am skipping from year to year. Okay. Okay, if there is no borrow. Okay, J and C means that is two categories are there, right? So subtracting higher number with lower number means, okay,